So 2 lectures ago, I had the technical issues. And so basically, I'm going to start by finishing off the things I didn't have time to mention then because of the technical issues. So it's a bit of a jump back to before Left Terrace's talk. So if you remember, we were at the point where we'd proved Lemans' theorem, the Pollaczek-Geringer theorem. So we'd characterized generic rigidity in 2-dimensional Euclidean space. And we did this by a recursive construction of 2 free tight graphs. And we'd already shown that the operations that we used then, 0 and 1 extensions, preserved minimal rigidity. So I did talk a little bit informally, a little bit about this, but I wanted to talk about further recursive operations to start this lecture. So I guess what I say here is that in some sense, we were lucky that 0 extensions and 1 extensions gave us all 2 free tight graphs. And this is really, we're going to see, but this is really one of the major problems that happens when you move to higher dimensions. So it's no longer true that you get all the graphs that you would like from these operations. So we talked about the d-dimensional versions of these operations, and we showed they preserved rigidity in dimension d. So if they got everything, we'd be really happy because it gives us everything, but they don't. There are lots of graphs that you cannot obtain from some small base graph by these operations in dimension at least 3. So before we move on and talking about dimension 3, I thought we'd talk about some further recursive operations, and then this motivates looking at planar graphs, which is what we'll spend most of this lecture doing. Okay, so the first one, I did mention it briefly, but here it is in more detail. So an X replacement operation, if you like, this is a version of 2 extensions. So 0 extension deleted 0 edges and added a new vertex. 1 extension deleted 1 edge and added a new vertex. X replacement deletes 2 edges and adds a new vertex. I say X replacement because it's specifically the case where the 2 edges you remove are independent. So the 4 end vertices of the 2 edges are all distinct. So if you like that, you can think of the 2 edges as making a little X. Okay, so we delete 2 edges, V1, V2, and V3, V4, and we add a new vertex V0 and D plus 2 incident edges. This is the D-dimensional version. So for example, in the 2-dimensional version, it would be 4 incident edges, and you must include the incident edges, must go to V1, to V2, to V3, and V4. So in dimension 1, forget about this operation, but in dimension at least 2, where it would be that to those 4, in dimension 3, it would be to these 4 plus 1 other. In dimension D, it would be to these 4 plus D minus 2 others. Okay, so we get in all these edges. Okay, so here's an exercise. If you want to have a go, consider the 2-dimensional version. So I delete 2 independent edges and add a vertex of degree 4 adjacent to the 4 endpoints. Show that this preserves generic rigidity in 2 dimensions. And so the idea would be to, if you remember the argument we used for 1 extension, we made this special position with a collinear triangle, extend that technique, and then you might think about why your proof does not extend for higher dimensions. Okay, and this maybe makes you wonder, does it work in higher dimensions? Actually, it's a hard open problem to show that X replacement preserves rigidity when D equals 3. I think, well, some people may not even conjecture it, to decide whether it does or does not preserve rigidity. I believe it's known via computations that there aren't small counterexamples to this. So if the graphs are small, then people have done some computations to show that there's no obvious counterexample. So the sort of expectation would be, I guess, that this preserves rigidity when D equals 3. However, it's not completely clear because it's known to not preserve rigidity all the time when dimension is at least 4. So there's a matroidal kind of rigidity book called Combinatorial Rigidity by Brigitte and Herman Servatius and Jack Graver. And in that, they go through in detail why it fails in dimension at least 4. And then the point is there are graphs which we know are dependent rather than independent that can be formed by this operation. So I think K66, the complete bipartite graph in dimension 4 is the smallest example. But in dimension 3 in the middle, it's completely open to show it. So you'll see if you do the exercise, it's quite an easy relatively easy argument in dimension 2, and it's false in dimension 4. So dimension 3 is right in the middle, where it seems it's too hard for us to know the answer yet, but we don't have counterexamples either.
And this would be for like general position.
Yes, so I guess I'm talking about graphs. So the X replacement would take, you can, so like I defined one extension where I defined the geometric version on the framework, you could define the special position that I'm intending here and show that it preserves rigidity at that special position. But what you really want to know is that if the first graph is generically rigid, then the result of the X replacement is generically rigid. So you really want to know about the generic framework.
Okay, thanks. And then, so if X replacement doesn't preserve rigidity in general, it's only of interest in 2 dimensions?
So if it does, so it doesn't preserve rigidity in dimension at least 4. In dimension 3, we don't know. If it didn't preserve rigidity in dimension 3, that would be really interesting. It would tell us something about what's hard in 3-dimensional space. So that would be really interesting. But okay, in dimension 2, we know it works, so it's a technique you can use if you need it.
You could almost say that X replacement is only interesting in dimension 3 then?
Yeah. So it's easy to show rigidity in dimension 2, and it's not really crucial for any of the results I mentioned in this course. In dimension 2, maybe it's not interesting. In dimension 4, it's false, so maybe it's not interesting. Yeah, so that makes sense. So you might wonder, so I said here specifically that the 2 edges were independent. So you can also have a version of a 2 extension where you delete 2 edges which are not independent. So you delete 2 adjacent edges. Here the 2 edges are adjacent, so you can think of them as a V. So this you can call a V replacement operation. So here you delete 2 adjacent edges, V1, V2, and V2, V3, say, and you add a new vertex V0, and again, D plus 2 incident edges. So the incident edges must go to V1, to V2, to V3, and then to the D minus 1 other places you want to go. So here's a picture of this operation when D is 2. So say you delete the edge V1, V2, the edge V2, V3, you add a new vertex V4, and you add it to, sorry, it should be V0. You add a new vertex V0 and you join it to V1, V2, V3, and to some other vertex V4. Okay, but notice what happened here. If I look at this vertex, here it lost 2 edges and it only gained 1. So the degree of V2 went down. So for example, if I give you a 2-3 tight graph G, so one that we know is minimally rigid in 2D, it's possible there's a vertex of degree 2. So it's possible I choose to do this move where V2 only has 2 incident edges, the 2 you see, and then in this graph, V2 has degree 1, which clearly can't happen in a rigid framework in 2D. So if the graph on the left was 2-3 tight and this vertex had degree 2, then this graph would not be 2-3 tight, it would not be minimally rigid. So this move can be more complicated. And so that's a sort of easy illustration of what can go wrong, but it can go wrong. And it's a bit more complicated reasons. You have to look at subgraph conditions to find a way to make this operation preserve the sort of tightness condition that you want. So there's a conjecture that's called the Double V Conjecture that sort of fixes this and conjectures it preserves rigidity in 3-dimensional space, the same way X replacement does. But again, that's open for 3-dimensional rigidity. Okay, the next operation I want to talk about is the vertex splitting operation. And so this is sort of motivated by topological graphy. So if you imagine you have a triangulation of a surface, then vertex splitting is one of the major things they use in that. So in terms of rigidity, Walter Whiteley introduced this operation, and he showed it preserves generic rigidity. So what is it? So you pick a vertex X, and we're going to split X into 2 vertices. So we have to think about a partition of the edges incident to X. So you pick your X and you choose D minus 1 edges incident to X. And then you think about the rest of the edges incident to X and partition it into 2 sets. So X has some d-1 neighbors that we care about, they'll be special. And then the rest of them are just however many there are, whatever it is. Maybe they're none, maybe there's lots. Maybe you partition them so N1 is all of them and N2 is empty, or some mix, however you like. But these ones we really care about, and we're going to specifically tell you what happens to those. And these ones are sort of, okay, they sort of come along for the ride almost. So we replace X by two vertices, X1, X2. That's the split of X into two vertices. And we replace every edge XW for some W in one of the two sets, N1 or N2, by an edge XIW, where XI is X1, if it was in XW was in N1, and it's X2W if XW was in N2. So maybe it's better just to look at the picture. So here's the vertex X we want to split into two. Here's the d-1 neighbors we care about, and then there's some other neighbors that we just partition arbitrarily into two sets, however you like. We split X into two vertices, X1 and X2. Oh, and I forgot to say this bit at the end. So the key thing is that X1, X2 are adjacent, and both X1 and X2 are adjacent to each of the Ys. So X1, X2, and Y1 is a triangle, X1, X2, and Y2 is a triangle, X1, X2, and YD-1 is a triangle. So that's what I was saying here. And then N1 becomes adjacent to X1 and N2 becomes adjacent to X2. So I think that is a bit of a mouthful, and probably I didn't explain it in an optimal way, but just to say it again, let's take the two-dimensional case. Here, what your d-1 for your y's is just 1. So you have X, you pick one special neighbor, and then you partition the other neighbors into two sets in some way. You split X1 into two vertices, X1 and X2. The X1 and X2 are adjacent. They're both adjacent to Y1. So this edge becomes a triangle. The edge from X to Y1 becomes a triangle, and X1, X2, Y1. And then we partitioned the other neighbors of X into two sets. Some of them go to X1, some of them go to X2. And then again, the sizes of those two sets is sort of irrelevant to the argument. They just have to still exist, and we go to one or the other of the two. So this is the operation. Okay, so is it clear what the vertex splitting operation does?
So we can kind of think about it as in reverse time, like the two vertices X1 and X2 had come together and sat on top of each other, including their edges. And we're just reversing time, like unperturbing it away from the degeneracy.
Sure, I think that's a good way to think of it. So going in this direction, which I'll call edge contraction. I think I'll define that in a bit, but let's just talk about it now. So there you take two vertices that happen to be in d-1 triangles. So this edge is in one triangle, two triangles, up to d-1 triangles. And if you like it's a graph, so I'm really talking just about graphs, but if you like geometrically, you just push X1 and X2 closer and closer together until they overlap. And then you make them just into one vertex and have all the adjacencies that you'd expect. And all these resulting sort of double edges just become single edges up here. Yeah. Okay, so the theorem that Whiteley proved, I've forgotten to put a year on here, but if you want to look up the reference and you can't find it, feel free to ask me. So what he proved was that if the graph is rigid in d dimensions and g' is obtained by the vertex splitting operation, then g' is rigid in d dimensions. This is all about. So it is true from R2 to R2, but it's an RD to RD statement. Obviously, if you're rigid in RD, then when you project down, you will be rigid lower down a dimension. So it was true with a 2, but it's sort of a much stronger statement to go from D to D if D is large. Okay, so I don't want to prove this theorem to you, but to give you a bit of an idea, the idea is a little bit like what Alex just said. So you start with this graph and you know it's rigid. You form this graph, but you choose the framework so that P of x1 is equal to P of x2, and let's say it's just equal to P of x. So really you have, on this picture, you have the two vertices on top of each other. And what this gives you is a zero length edge, which is not good. So say you were minimally rigid before, that zero length edge will be a zero row in the rigidity matrix. So it won't have full rank anymore. It'd have the right count to be minimally rigid, but it'll have a zero row, so it can't be. However, what Walter does is look at a different kind of matrix to a rigidity matrix called a direction network is one name for it, and puts a row for this zero length edge, replaces it with a direction row in some sense, and then shows that you can use this to when you move from the coincident to the more generic position, you will have the right rank. That the complication really comes from having this zero length edge. So in a moment, I'm going to give you a variant of this move which doesn't have that. And in that case, the proof is kind of an exercise. Okay, so there's maybe...
Tony,
yeah.
in algebraic geometry, we probably would have called that blowing up the vertex, giving an extra piece of kind of velocity information or tangent information that indicates kind of what direction the x vertex is splitting in.
Okay.
Could be
Thanks.
fun to think about it that way.
Okay, so I mean, this again in 2 dimensions we know everything. So this is a sort of an operation of the intention of being useful when we're looking in dimension at least 3, but it is going to be useful for us in a moment because I want to talk about planar graphs that are 2-3 tied. But before that, as I said, I want to just introduce this sort of the same operation, just a slight variant. And this was also introduced by Whiteley, and he calls it spider splitting. So I'm using that name too. So here, again, you have your partition N1 and N2 of your vertex that you want to split. This time you have D vertices over here instead of D minus 1. And when I split into V1 and V2, so some of the neighbors of V go to V1, some go to V2. All of the special ones, Y1 up to YD, become adjacent to both V1 and V2, but there's no edge between V1 and V2. So there was one more up here, which allowed me to not have the edge in the middle between V1 and V2. So this is, for example, that this doesn't, the previous operation introduced a triangle. So if you're interested in bipartite graphs, say for some application, then this move might be useful, whereas that one couldn't be because it introduced odd cycles. So in this case, there is, oh, and let me just say again, just to make sure. So in D dimension 2, D is 2, so there's just a Y1 and a Y2, and I think it's easier to draw it looking like this. So I split V, so I did have a path of length 2, Y1 to V to Y2, and I split that into a 4 cycle with 2 new vertices, V1 and V2 replacing V, and the edges incident to V split among V1 and V2. So this is I think a nice operation. To show that this one preserves infinitesimal rigidity, that's this exercise that I'm suggesting here. So here you can do the same thing I was just trying to explain. So you put P of V1 and P of V2 in the same place where V was. And so in fact, let's just do the 2D version, and I'll do it in an extra step. So I have this, and I'm going to do the operation, but I'm not going to split the edges into the 2 parts. I'm just going to leave them all on one side. So say there was 5 edges incident to V here, I'm going to put them all incident to V1 and just put V2 there. Then that operation is easy because this is a 0 extension, and we talked about this operation as preserving rigidity. And it still preserves rigidity if you put V2, if you put P of V2 on top of P of V1. So at that, and then at that coincident realization, you use the fact they're coincident, at least I'm telling you can use the fact they're coincident, to pick an edge like that, delete the row for that edge from the rigidity matrix, and input this row in the rigidity matrix. And you can do that by sequence of row and column operations on the rigidity matrix. So, I mean, it's maybe not so easy, but if you want a challenge exercise, you could try and find that sequence of operations, but it's just Gaussian elimination. So it might not be the most fun exercise if you don't sort of spot how to do it straight away. And you can do that one by one. You start with this edge and then pick a second one up, and pick a third one up and a fourth one up, as many as you need, and just go one by one across. And obviously they're rank preserving operations. Okay, so that's my list of additional operations that occurred to me about d-dimensional space. Maybe there are others, but I didn't think too hard. These are the ones that are well known, I think. So as I said, I wanted to use planar graph, use the vertex splitting operation for planar graphs. So obviously a planar graph is a graph that you can embed in the plane so that no pair of edges cross. So edges only meet each other at end vertices when the two edges are incident to the same vertex. And so there's a distinction that needs to be made between a planar graph, which is just a graph which it's possible to embed in the plane, and a plane graph, which is a graph and an embedding with no crossings. So K4 would be a planar graph, and this particular drawing of K4 in the plane shows that it is a plane graph. Okay, so there's a bit of a distinction, but we're going to work with plane graphs. And what I want to do is look at two free tight plane graphs and generate them all by vertex splitting operations. Okay, so the idea here is that there are times when there are problems in rigidity theory and in discrete geometry more widely where you have to restrict to planar graphs or plane graphs, and you want to stay within that class. So if I just give you 0 and 1 extensions, then it's possible I start with a planar graph like this one. And remember in lecture 3 or 4, I did a sequence of 0 and 1 extensions that got me to K33, which is non-planar. So if you want to be careful to maintain planarity and stay within this nice family, then you need to think a bit harder. And so two free tight graphs or minimally rigid graphs in the plane could be planar. They could be some nice planar ones, or they could be non-planar. So we want to now, rather than generate all two free tight graphs, we want to generate a subset of those, which means that when we're doing our reductions, it's harder to maintain the property of being within the class because it's more restrictive. So we have to work a little bit harder to make sure we can get them all. But that's the sort of aim of the next, I don't know, 10, 15 minutes, I guess. Okay, so as I guess I sort of hinted at, we're going to show that vertex splitting is sufficient to generate all plane minimally rigid graphs, which are plane two free tight graphs. But the vertex splitting operation, I had this, let's just draw the 2D picture. I had this partition of these two sets. So if I choose these in a sort of not nice way, I could break planarity. So I have to be careful to use the sort of cyclic ordering of the neighbor set of the vertex I'm splitting into x1, x2 to make sure that when I don't pick up I don't have something like this and decide to move this edge over to the other vertex and hence break planarity in a bad way. Okay, so I just need to augment the definition of vertex splitting to what I call plane vertex splitting, which means exactly what I've just tried to say. So the partition of the two sets, so don't worry about the ones up here, but the partition just of N1 and N2 respects the natural cyclic ordering of the neighbor set determined by the plane embedding of the smaller graph. So the smaller graph has a plane embedding, and we're going to just move the x into x1 and x2. We do that close to each other, so it's within some nice part of the plane embedding, and as long as we respect the ordering when we're determining which edges are incident to x1 and which are incident to x2, then we will result in a plane graph. So under this assumption, vertex splitting does take one plane graph to another plane graph. Okay, so hence it's true because we know that vertex splitting preserves two free tightness or minimal rigidity. by Whiteley's theorem, we know that every graph we're going to get from K2 by these plane vertex splitting operations is a plane minimally rigid graph. And what we want to do is show we get all of them. So to do that, we move from minimally rigid graphs and Whiteley's theorem to working with two free tight graphs, okay? But the converse is more involved, and I decided actually not to go through the full proof. I'm just going to give one or two results and a sort of idea of the rest of the argument. So what is the converse? So remember, in 2 dimensions, excuse me. So in 2 dimensions, the converse, as we sort of said before, is we take a triangle, and let's say it has an edge E between U and V, and so there's some other vertex, I forget what I'm going to call it, maybe W for now, and I contract E down to, so U equals V is some new vertex, we give it another name, and W is here. So we need, first of all, to know that there is a triangle face in our graph. We need this face that's a triangle to have a chance of contracting. If, for example, a 2 free tight graph could be triangle free, like K free, but the plane assumption is going to help us there. Okay, so here I just say what I just tried to do in that picture. We take an edge of a triangle face in some given plane graph. Then we talk about the contraction of this edge E, which identifies U with V and discards the edge between U and V, which you can think of as becoming a loop. So you discard that. And you also you had 2 edges, UW and VW, which become 2 edges between the UV vertex and the W edge. So you discard one of those. And it's a contraction, so I'm going to use G contract E to denote the result of if I apply a contraction of E to the graph G, then G contract E is the resulting graph. Okay, so the first thing I want to prove, and this is a very easy lemma that I guess you probably might have seen in undergraduate courses, I guess roughly, if you express it in the right way. So every plane 2 free tight graph with at least 4 vertices contains 2 triangle faces. So obviously if it had less than 4 vertices, then my 2 free tight graph is either this, which only has 1 face that's a triangle, I guess the outer face, but I don't really want to think about the outer face, or you have a single edge which has no triangles. But as long as it has at least 4, then this becomes true. The plane assumption is clearly necessary from K free, as we said. And this example that I drew before, so this is the triangular prism graph. It's the Cartesian product of K3 and K2, if you're a graph theorist. But this illustrates that 2 is tight because it has exactly 2 triangle faces. The other faces have size 4, 4, and 4. So this is this lemma is sort of best possible. We want to find triangle faces to contract, and the most we can guarantee is there's 2 of them we could possibly contract in a big graph. So why is it true? Well, it's just a simple calculation. We take Euler's formula, which applies to any connected plane graph and tells us the number of vertices minus the number of edges plus the number of faces is equal to 2. 2 free tight graphs are connected, and we're interested in plane 2 free tight graphs, so the hypotheses are fine. So let me suppose that the lemma is not true, which means that there exists some G, which is plane 2 free tight, and at most one of its faces is a triangle, okay? So 2 free tight tells us E equals 2V minus 3, which tells us 2E equals 4V minus 6. So that's easy. So we know that twice the number of edges is at least the size of the faces. So in general, you would have 3F because the faces would be at least triangles or bigger. But we know that at most 1 is a triangle and every other one is not. So we actually have 4F because the smallest face would be size 4, except for the 1 triangle we allow. So it's 4 for everything apart from 1 where it's 3. So we get 4F minus 1. Okay, so now I times this thing by 4 and substitute it in. So I'm going to replace 4F with 8 minus 4V plus 4E, and the 1 takes the 8 to a 7, and that gives us this equality. And then I can again substitute this in for E over here and just simplify. And so now I know that 4V minus 6 I didn't do the calculation out, but hopefully it's not too fast. 4v minus 6 is greater than or equal to 4v minus 5. So, which is obviously a contradiction because this thing is definitely bigger than this thing. So we've proved that we have at least 2 triangles in our graph. So now we know we can always find one. The key question is, when is the contraction by this edge E, when does it result in a smaller 2-3 tight graph? We know it will result in a smaller plane graph, so that's okay. But there are 2 problems that might prevent it becoming the contracted graph being 2-3 tight. The first one is that, well, we know E is in a triangle, but what happens if it's actually in 2 triangles? Then when we contract, we do the sort of operation up here, and that's fine, but we have a second vertex that becomes adjacent to the contracted vertex twice. And that means we either have a multigraph, which is no good, or we have to discard an edge, which throws the count off. And so we don't have E equals 2v minus 3. So if your edge is in 2 triangles, that's bad. And the second thing that can happen is that, well, if there's not 2 triangles, then the edge in a triangle must be in a unique triangle, say on UVW, where the edge we want to contract is E equals UV. And then G contract E could contain a subgraph which fails the sparsity condition. So we could have some subgraph which has too many edges to satisfy for the graph to be 2-3 tight. Since it was in a unique triangle, it's easy to see that we've removed 1 vertex and we've removed 2 edges. So E equals 2v minus 3 persists down to G contract E. So there must be some subgraph that's gone wrong. So either we break simplicity or the top count, depending on which way you think about it, or we break sparsity, okay? But what we're really going to do is show that these are really one case, because I'm going to express this one as this, which I'll say in a moment, but then what's happening with the second triangle was really a smaller graph which has the same property except x is size 3 as well. So we can deal with both of these blocks at the same time. But first of all, what's this break of sparsity? What we're going to prove is the only way this can actually happen is if there's a critical set. Remember, critical meant that I of x is 2x minus 3. And so one of these sets with u and v, so it contains u and v, but it doesn't contain the third vertex of the triangle, and it has at least 4 vertices. If it only had 3 vertices, it would be u, v, and something else, and hence it would be exactly the one we said for the simplicity problem. Okay, so we have, this is what we're going to prove, that the only things that can go wrong are these 2. So that's what the lemma says. I take a
Sorry,
2-3.
Tony.
Yeah.
Could we pause for a second? Could you just scan back up a bit? Yeah, there. I'm still taking notes if you don't mind.
Sorry. Yeah.
So u and v are an x and w is not an x.
Yeah, maybe this is a good time just to ask if anyone has any questions.
So are you saying that this critical x implies that there exists that blue triangle that you've got? Or...
No, sorry, the blue triangle is just one possibility, and that's the other thing. But so I guess what I'm saying is, if this x exists, so a critical set with these properties, then when we do, this is in the graph G, then when we contract E, this edge UV, then x will become, u and v will become identified. So we'll lose 1 vertex, but in E will disappear, so we'll lose 1 edge. So we had this, but we lose 2 from this side, 2 times 1, and we lose 1 from this side, so we cause a problem.
Okay.
So with -2 here and -1 here, so this becomes bigger than and becomes a violation of the 2-3 sparsity condition.
Okay. Great, thank you.
Okay, so the lemma. So this should say let G equals V be plane 2-3 tight, and let E equals UV be an edge. Then we do the contraction. Oh, I guess I don't. I mean, I can put plane in or not, I guess. So maybe it doesn't matter. But I really only care about it in the plane case. So either ignore or don't the blue. I think it's probably irrelevant for this proof, but we'll see as we go. It's not. I don't think plane is particularly important for the proof. Yeah. So we could ignore plane, but you should keep it in mind because it's what we're doing. So take a 2-free tight graph with an edge E equals UV. Then G contract E is 2-free tight. If and only if there's a unique triangle in G containing E, so that stops us having this contraction, which would have caused an issue, as I said. And the second thing is there is no critical set with the properties we just talked about. So there's no critical set containing the two end vertices of E, U and V, not containing the third vertex in the triangle, and having at least 4 vertices. And the at least 4 vertices is just a kind of trivial assumption, because if it had less than 4 vertices, it would be a 3 vertex graph and it would be the other option. So it's not saying 3 vertices is somehow good. It's just saying that's in the other part of the options. Okay, so first we're going to suppose that the graph is 2-free tight, and we're going to show that one of these things, that neither of these problems could have happened. Okay. So since it's 2-free tight, this certainly didn't happen. So E belongs to a unique triangle. We've already talked about that. So for a contradiction, let's suppose the other thing fails. So suppose there is a critical set with UV in X, W not in X, and X at least 4. And this is kind of what I just said up here, just making this argument formal. Then the edge E is an edge of the subgraph X, the subgraph into G induced by X, and it belongs to no triangle in this because of this condition. Hence, GX contract E has 1 less vertex and 1 less edge. But since X is critical, this gives us that we lost 1 from the edge side and 2 from the vertex side, and hence we create a strict inequality which contradicts our sparsity assumption. Okay, so we assumed it was tight, and then we found this bad subgraph. So that direction is the easier one. So conversely, suppose there is a unique triangle containing E, and there is no critical set with the stated properties. Okay. So now if we want to suppose that G contract E is not 2-free tight, and let's let V dash denote the vertex of G contract E we get by contracting E. So we contracted E equals UV into some new vertex and we call it V dash. Since G is 2-free tight and E is in exactly one triangle, we know that the top count is fine. So it follows that there is some set in this not 2-free tight graph G contract E, so a set called Y, which has at least 2 elements, and the number of edges in it violates the 2-free sparsity condition, so it's at least 2y minus 2. Okay, so since UV is in a unique triangle, all the subsets containing V dash and W, so remember this is W, this was UV, and now it's W and V dash after the contraction. So all subsets containing V dash and W and all subsets not containing V dash satisfy the sparsity requirement because they just exist in G, or if it contains W as well, you lost 2 edges and 1 vertex, so they're all fine. So it must be that Y has size at least 3, it must be that V dash is in Y, and it must be that W is not in Y. So now that we know that, we take our X, we take Y and we subtract V dash and we add, so we subtract V dash and we add back U and V to Y, and we get Y minus V dash union UV, then call that X. Because of this count and the fact that X is a subgraph of G, it must have been that there was an equality here, and hence X is critical, and we have the properties we want. So we finished this sort of characterization of when a contraction is 2-free tight. So we've shown that one of these 2 options are the only things that can go wrong. Okay, are there any questions about that? I think that's the only real proof I'm doing in this plane section. The rest is going to be just a sort of discussion and a sort of sketchy. Okay, so as I say, it is a bit more involved than what we did for 0 and 1 extensions, but what can be established, and the reference is Fekete, Jordan, and Whiteley in 2004, is that a plane graph is 2-free tight if and only if it can be generated from K2 by a sequence of these plane vertex splitting operations. Actually, there's an alternative reference from John Owen and Stephen Power, but they worked with free connected plane 2-free tight graphs. So they were working within an even more restricted class. And so the general, not when you allow non-free connected things, this is the correct reference, but there's a second reference that does a similar thing. Okay, and obviously because vertex splits preserve rigidity by Walter Whiteley's argument, this tells us, I guess if you like, another way to tell us infinitesimal rigidity in the plane or planar case. Okay, so I want to give you the idea of this proof, but not any of the details. Okay, so I mentioned in the first lecture of this course that some of the, especially the combinatorial parts of this, I took some inspiration from the presentation in an article of Tibor Jordan's. So if you look back at that article, he goes through all the details and proves this in detail. So if you want to look at the rest of the steps, it's not particularly hard, it's just quite long and technical. So I just want to give you the idea and then we'll move on. Okay, so what I'm going to say is that a critical set X is called a blocker for a particular edge, E equals UV, in some triangle, if UV is in X, W is not in X, and the size of X is at least 3. So if the size of X is 3, that's saying that the edge in this triangle is in a second triangle, and if X is at least 4, it's what we said as the second problem where sparsity would fail. So we want to now choose an edge in a triangle, which we know must exist. We proved that. We know triangle faces exist. And if there are no blockers, we're done by the lemma we proved. So we look at a blocker must exist, and then we work with these blockers, okay? So we know a triangle face exists. Let UVW be such a triangle. Suppose there is a blocker, so it's not contractible. Then if this particular edge UV is not contractible, then we can choose a maximal blocker, where maximal means number of vertices. So X is the largest number of vertices, such that it's a blocker for the edge UV, so such that it contains UV, not W, and is a critical set. So we pick a maximal blocker for this particular edge F, and our aim is to show that we can look at the subgraph induced by this blocker X. This is, by the way, is a 2-free tight graph because X was critical. We look inside that 2-free tight graph. It's plane because it's a subgraph of a plane graph. So this GX is a 2-free tight plane graph itself. It has a triangle face. And so what the aim is to show that some edge in there is face contractible, but not just face contractible in GX, but face contractible actually in G as well. Okay. So hopefully that's clear. So we have the blocker gives us a subgraph, which is one of these plane 2-free tight graphs itself. We know there's a triangle face in there. We want to show that there's some edge in there which we can contract in the entire graph G, so it has no blocker in the entire graph G. Okay, so I guess I said this. So since X is critical, GX is 2-free tight, and we have a plane embedding of GX. Okay, and so really this is I guess is all I'm saying, because the rest is just very brief. So an edge of GX is proper if it's an edge E in GX is proper if it's not equal to the one we know is non-contractible, because F is not contractible. So that's where we found this blocker. So we know it's an edge in the subgraph is contractible if it's distinct from F, and its face contractible in GX, and the triangle face in GX is also a face in G. Okay, and if we have those 3 properties, it's not so hard to see that such proper edges are actually face contractible in G. So if we can show that there is an edge in GX which is different to the edge we can't contract F, and it's contractible itself in GX, and the triangle face of GX is also a face of G, then we will be finished. And so the work is really to show that property. But as I say, I don't want to go into the details of that, or I didn't when I was writing these notes, but it occurs to me there's not long left to say the next things I wanted to say, so maybe I should have. So I'm going to flip to a different OneNote document and say a little bit about three-dimensional rigidity, but does anyone want to ask any questions about plain two free tight graphs or vertex splitting before I move on? Okay, so I guess there isn't a question. I think I have the chat available, but I don't see any questions coming in there either. So yeah, so if I'd kept up to pace, this would have been where I'd started this lecture, but I am behind. So I want to just start to give you some hints as to what happens in higher dimensions. So remember that if you have linearly independent rows in the rigidity matrix, or if the rigidity matroid is independent, then the rank of the rigidity matrix is at most this sort of Maxwell bound. So d mod v minus d plus 1 choose 2 whenever v is at least d plus 2. And if it's smaller, it can be a complete graph, and the count is very slightly different. If we want so now we want to consider rigidity in d dimensions where d is at least 3. So the first thing I want to do is define the same class of graphs as two free tight graphs. So that was the case when d equals 2, but I just want to do it in general. So there it was 2 and 3. So now our d comma d plus 1 choose 2 sparse graph is a graph such that the number of edges in any subset of the vertex set with at least d plus 2 vertices in it, any x of size at least d plus 2, it must be true the number of edges induced by x is at most dx minus d plus 1 choose 2. And then we can, as we did for two free sparse and two free tight, we can say a graph is d comma d plus 1 choose 2 tight if it's sparse and has the total number of edges is the max possible. E is dv minus d plus 1 choose 2. To avoid having to keep saying d plus 1 choose 2, I'll probably, maybe not consistently, but I will try to be consistent in sticking to saying d sparse instead of this d comma d plus 1 choose 2 sparse, and saying d tight instead of d comma d plus 1 choose 2 tight. So d sparse means you have this inequality for all big enough sets, and d tight means you're d sparse, and e equals dv minus d plus 1 choose 2. Okay.
Tony, just a quick question. If you're d tight, does that mean, does that imply anything about the tightness of the subgraphs, or just that they're sparse?
So which subgraphs? So you need the sparsity condition for all subgraphs?
You need the sparsity condition for all subgraphs, but does it imply equality for all the subgraphs?
No, so
I guess not, yeah.
So for example, d-tight graph, saying you're a d-tight graph is not strong enough to control the girth of the graph. So most of the examples you would see if I drew, say, a 3-6 tight graph when d equals 3 would have triangles, but they could have, it could be arbitrarily large, smaller cycles in the graph, so that they don't have to have any proper subgraphs that are d-tight themselves necessarily. So some will and some won't. So no, you don't get any information about how tight subgraphs are just from the d-tight condition.
Sparsity is preserved for subgraphs.
Sparsity,
not tightness.
Yes.
Okay, great.
So remember that what I'm still calling Lemans theorem, the Polacek-Geringer result, said that minimally rigid in 2D was exactly 2 free tight, or what I'm now calling 2 tight. So the analog would say that every d-tight graph is minimally rigid in RD. However, this is not true. And this is really the main motivation in combinatorial rigidity, is to trying to find an analogous statement. So trying to find which d-tight graphs are minimally rigid in RD, especially when D equals 3. So let me just try and quickly show the smallest example. So for all dimensions. So first of all, for D equals 3. So the smallest example of a D-type graph, which is not rigid, so a flexible D-type graph, is what is commonly referred to as the double banana. It's this graph on, 8 vertices. So it's the point that it's flexible should be easy to see. The 2 vertices I've highlighted, U and V. The line through those acts as a hinge, and so you could fix the banana on the left and rotate the other one around, and so this gives you a continuous deformation, infinitesimal deformation, whatever you like. This just moves infinitesimally and continuously, so this is definitely not rigid. But if you count up, it's got the 8 vertices and it's got 18 edges, so 3/8 minus 6 is exactly right, and all the subgraphs work as well. So this is free tight, but flexible. So it's not minimally rigid in R3. And so I say, yeah, the pair UV acts as a hinge around which you can rotate one of the bananas. So it's kind of easy. But this example you can generalize. So, and in particular, I guess one thing it says is that free tight does not imply free connected. And if you're rigid, you certainly must be free connected, because it did not matter what was this side or what was this side. All that mattered was I had these 2 vertices that separated things out. And so if you have such a 2 vertex separation, i.e. you're not a free connected graph, then you can always do this rotation of one component about a hinge. Okay, so let me generalize a little bit. So I want to define a 2-sum. So I give you graphs G, G1, and G2 with the respective vertex and edge sets. Then we say that G is a 2-sum of G1 and G2 along the pair UV if the 2 graphs G1 and G2 intersect exactly in U and V. If the edge sets, so if it's a UV is a common edge, so this shouldn't be, comma shouldn't be there. If UV is an edge in both G1 and G2, and the vertex set of G is the union of the 2 vertex sets, and the edge set of G is the union minus UV. So in this picture, if you can still see it, I had K5 as G1, K5 as G2. I took the union of them and I deleted the edge between U and V. Okay. So this is a 2-sum operation which you can use to create lots of counterexamples, lots of D-type graphs which are not minimally rigid in RD. So I'm sorry for going a little bit over time, but I just want to finish with this picture basically to show this example extends to all dimensions. So I'm going to do the 2-sum, sorry, I'm going to do this summing operation, but I'm going to have more vertices in the intersection. So I'm going to take G1 and G2, instead of being K5, to be KD plus 2. I'm going to take the intersection to be the complete graph on D minus 1 vertices. And I'm going to pick some edge in the intersection. And I'm going to say B for bananas, I guess. So B, D, comma D minus 1. So the D is that we're in dimension D, and the D minus 1 is the size of the intersection, to be the union of the 2 graphs minus the edge E. So in other words, I had KD plus 2, which is these D minus 1 plus 1, 2, 3 vertices, D plus 2, and on the other side again, D minus 1 plus 1, 2, 3 vertices for KD plus 2, the D minus 1 vertices in the intersection, and missing one edge E. So every other edge is present in here, and the 3 vertices here are adjacent to everything in the D minus 1 vertices here, but no edge like that, they don't exist. And these ones are adjacent to absolutely everything. The ones on the right adjacent to everything in the separating set as well. But again, no edges from the triangle on the right to the triangle on the left. And so you can do it. I don't have time to really do the details now, but it's sort of elementary just to count up the number of edges. This is D tight. And the same way you can have a hinge through 2 points in R3, you can have a hinge through D minus 1 points in RD. And so it's still flexible. And in fact, it's provably the smallest D-tight but not rigid graph in any dimension. So for all D greater than or equal to 3, you have the smallest flexible graph that is D-tight. There's D-tight but flexible on D plus 5 vertices. Okay, so I should stop there. Happy to take any questions. And on Friday, I believe we'll have another guest lecture, but that will become clear on Friday in the talk, whether it's me continuing with 3D rigidity or whether it's Daniel Bernstein talking about the rank function. So as I say, any questions, please ask. Otherwise, thanks for coming, and I'll see you on Friday.
So I've got a question about this analog of Lemans theorem that we're searching for.
Okay.
So Lemans theorem says that every D-type graph is minimally rigid in RD, and that
No.
I guess
So
it's false.
Lemans theorem says every 2-type graph is minimally rigid in R2.
I see. Sorry. Yeah, the analog would say that we're searching for is some characterization of minimally rigid graphs in RD. Is that the aim?
Yes.
Okay, and what we know is that rigid graphs, say in R3, in D3, are in particular 3 connected.
So we know that minimally rigid graphs in R3 must be 3-tied, but they also have extra properties. And just as one example, I said they must be 3 connected.
I see.
But there are much more complicated things would have to add to fully characterize, and we don't know what they are.
I see. So is there some result that we could cite that would, I guess maybe this isn't really a well defined question, but I'm wondering whether there's a finite list, like there's a finite list of conditions, 3 connected, 3 tight, keep adding in conditions until you get to minimally rigid. I mean, I guess the reason my question isn't even well defined is you could add minimally rigid in as your requirement, and then you're done. But somehow I'm thinking of this of the kind of forbidden minors approach to characterizing certain things in matroid theory. That says that in roughly that every matroid result can be characterized using a collection of forbidden minors, and that forbidden minors list, I think, can be is finite in each dimension. And so the question in some sense is there some kind of analogous result that would allow us to say, yes, we know that there's some finite set of conditions here that would guarantee, that would characterize minimal rigidity?
So it's not an answer to your question, but just to point out, for anyone who didn't know, rigidity is not minor closed. So we can't talk about forbidden minors, that's for sure. You can easily go from flexible to rigid or rigid to flexible when you do the contraction operation, or even subgraph operations can go from rigid to flexible. So I guess what's hoped is that there is a combinatorial, purely graph theoretic characterization which leads to a faster algorithm, and how you can express that graph theoretic characterization, I really have no idea. Well, I guess there's conjectures that would lead to it having some nice closed forms, and what I will show in my next lecture or two will be special cases, classes of graphs where it is very well understood. But most of these special cases I'll explain are simply, oh, we've made the graphs nice enough that this D-type condition does work. Mm-hmm. And the examples like these ones that I talked about that are wrong are kind of hard to fix. So it's not as simple say as let's add 3 connected and those examples disappear, because you could just take the particular one, say in R3, and you add 1 vertex and join it to these three, and now the graph is free connected, but it still has the same subgraph as before, so it still has the same dependence in the rows of the rigidity matrix. So even that is not a sort of sensible. I mean, it's one step forward, I guess, but it's trivially still the same problem exists.